If you zoom in past the electron cloud, straight into the dead center of an atom, you hit the nucleus. It is impossibly small, totally invisible to the human eye, and governed by quantum forces so complex they almost defy physical intuition. This presented early physicists with a massive problem. How do you accurately calculate the mechanical energy of an object that you can never actually put under a microscope and measure directly? In 1935, Niels Bohr and George Gamow proposed a radical workaround. Instead of wrestling with the incomprehensible math of quantum mechanics, they suggested physicists stop treating the atomic nucleus like a microscopic puzzle entirely. They introduced the liquid drop model. Their hypothesis argued that the mechanics of a nucleus could be perfectly calculated if you treat it exactly like a simple, incompressible droplet of liquid. If this metaphor holds up, the physics governing a puddle of rainwater provide the exact coordinates needed to predict how a nucleus will react under extreme pressure. The comparison starts with geometry. Both liquid drops and atomic nuclei naturally assume a spherical shape. In a drop of water, this shape is driven by surface tension. Molecules inside the drop interact tightly with their neighbors through cohesive and adhesive forces, pulling the liquid inward into a tight sphere. This diagram shows how that maps to the microworld. Inside the nucleus, a similar surface tension exists, driven by the strong force. Nucleons interact fiercely with immediate neighbors to reach a saturation point, creating that same spherical volume for maximum stability. Next, water is functionally incompressible. Whether you have a single drop or a whole bucket, the density of the liquid remains constant. The nucleus behaves the exact same way. Its density is constant regardless of the total mass of the atom. Energy inputs align perfectly too. If you heat a single water droplet, it absorbs that energy and evaporates. If you supply energy to a nucleus by bombarding it with external particles, it performs nuclear reactions and emits radiation. Even violent physical disturbances mirror each other. Oscillate a liquid drop fast enough, and the instability forces it to split. Disturb a nucleus with an external factor, and it splits apart in a nuclear fission reaction. Macro-world physics provide the literal blueprint for the forces churning inside the atom. To prove this theory, physicists translated those physical observations of water into hard mathematical variables. This is the exact formula they built, the semi-empirical mass formula. This chart breaks down the variables. We start with the massive green volume energy column, driven by the strong force. But the formula chips away at that total, deducting surface energy, Coulomb energy, and symmetry energy. An atom's total binding energy is ultimately a mathematical compromise. It is a constant battle between an ideal, bound volume and destructive forces pulling it apart. Let's run an extreme stress test on this liquid drop metaphor. This is the data for nickel-62, widely known in astrophysics as the most tightly bound nuclide in the universe. To test the formula, we only need the raw counts from the nucleus, 28 protons and 34 neutrons. We plug these counts into our liquid properties. The dashboard calculates competing forces, pitting positive volume energy against negative surface, Coulomb, and symmetry deductions. Tallying the gains and losses, the formula spits out a final total binding energy of 548.5 mega-electronvolts. Scientists can take a physical sample of nickel-62 and measure its exact real-world atomic mass using a mass spectrometer. This diagnostic table compares these worlds. On top is the measured physical mass. Below is the theoretical mass derived from our binding energy equation. The variance between a 1930s water puddle metaphor and precise atomic reality is roughly 0.005%. By reducing microscopic systems to a recognizable macroscopic concept, physicists successfully mapped reality, proving that the simplest physical models can accurately predict the most complex interactions in nature.